However, the question basically is that you have a function z of x comma y to be a square root of xy, and you have to show there are two questions, that dz of dx is equal to 0 and dz at 0. 0. At the origin they're both 0. Okay. And then you have to show that at the origin at 0, 0, so this is problem 6 in page 269, App Store. So at the origin, the question is, do we have a tangent plane? Okay, we have, so the definition of a tangent plane is this.
Was it that heat made us confused?
Yeah, when you look at this and you see the partials are 0, this is you don't have any plane, because the partials are automatically 0 at the origin. You don't have anything there, so you don't have a plane. And that, if you also intuitively want to see, the hint was that if you take a slice of the surface, so this, we look at the function, only 0 level set of this function has only one point. So if you take, yeah, so if you take a slice with the xy plane, you have only one point at the origin, because this is z of square root xy. So only value 0 of z can only be attained. Well, not necessarily, no. You can have x equal to 0 and have a z. Oh, okay. You can actually have other points. X equal to 0 will also.
We cannot draw family of curves.
Yeah, we cannot draw family of curves. Yeah. Yeah. We need a family of curves. That's one thing. But you can have 0, no? You can have 0 for x equal to 0 and y equal to 0.
Yeah.
But
x-axis and y-axis and at the origin.
How the curve looks like then? For the
only x-axis and y-axis.
Our argument bhul to tahole. I can't give a level surface. I can't give a level set there. Yeah. How does it look like then? X equal to 0, on the x equal to 0 line, you also have z equal to 0. So you have xy, you have xy axis actually. You do not have level curves, but you can approach them, no?
But we cannot have any arbitrary level curves.
Yeah.
That was the proof, that we can have any arbitrary level curves on the level set. If it the proof was put 0 at once. We can. How do we reach arbitrary level curves?
Which one?
I mean that you said, like del z del x 0. Verify that are both 0 at once.
You just have to apply the limit. You can apply, just go ahead and take the derivative of that thing and put 0, 0 at the, take a derivative and put the 0, 0s in it. Because x, y, both of them are going to 0, it is identically 0. You don't have to worry about the mod derivative here, because y goes to 0. So ultimately the derivative will be 0. So that holds, but our argument of what I told you is not going to be right, because it has more points than at the level set. You have the x-axis 0 is a level set. X-axis 0 is the level set. If I say xy. If I say xy, y is in the level set. X is also in the level set. Because
we can only have two tangent but we need.
No, it's still infinite amount of them. Yeah, yeah.
For the plane.
Yeah, but the partials are 0.
Partials are 0 and
identically 0. Yeah.
Sorry, tangent.
ওটা কিভাবে use করবা? That's what I'm saying. How can you use that here? ওই যে arbitrary না হইলে দুইটা দিয়ে কেমনে করবা আর কি? Can you do that? Also, that's intuitively makes sense, no? Because you can have arbitrary things, yeah.
Yeah, we cannot have arbitrary because we need arbitrary lines for the construction of the planes.
Yeah. That's true. But yeah, that's intuitively clear. But how do you put it in mathematics? Maybe okay. So maybe in this equation, what are you looking for is y minus 0, x minus 0. On this line and on this line, but on those two lines the derivative is 0. It is 0 everywhere actually if you approach that point. So ultimately that's 0. You do. Yeah, I think that you can put it into the words. Yeah, so instead of a point we have two lines. What he said is right. You do not have arbitrary level lines, level curves. I was going for that, but আমার একটা পয়েন্ট হবে না, এখানে okay, so that's done. Sufficient. Okay, so I have to erase all of this. আমার আসলে কি erase করার দরকার ছিল? Maybe not. No? Okay. Okay. So I hope everybody looked at this. Specific case, why one needs to care for sufficiency conditions for the equality of mixed partial derivatives. So mixed partial derivatives are something like this: d1, d2 of a scalar field, something of a scalar field. So let's say f is a scalar field, then this is really d1, d2 of f, and d21 of fxy really means we have a d2, d1 of fxy, right? So the question is, are both the expressions equal? It's natural to expect to be equal if you are just computing things and not defining things properly. However, if you define things properly, you'll see they're not actually equal for arbitrary situation. The question is this. Actually, the answer is no, on general grounds. So you can come up with an example. So this no proof is this proof by count. Suppose this is true. Let d1 to d21 fx, so let this to be true. Then give a counter example. Then you can come up with a function. So then we can construct a scalar field which is from say R2 to R via or defined by this fx comma y to be equal to xy x square minus y square divided by x square plus y square for x comma y not equal to 0 0, that's the origin, and it's 0 at the origin. Now then you can verify that using the definition of d12 and d21, that d12 is plus 1 and d21 for this function will be minus 1. Okay, where when you actually xy to arbitrary now, these are 0 at the origin.
So what does this look like? This function is so we have okay. This is a very specific example.
Yeah, this is an
So
yeah.
can we generalize that?
Yeah, so this is a proof by counter example.
Yeah, I understand. But also, okay, cool.
So that statement is not true. So there are four ways of proving things. One is direct proof. One statement leads to another. One is induction. Very favorite for everyone. If you have a formula, you can test it. So in path integrals, we prove something like using induction. Always. In path integrals, we have a formula for Gaussian integral, and then we prove it for n equal to 0, n equal to 1, and then.
Yeah, induction. There's also proof by contradiction.
The path integrals.
No, no.
Oh yeah, in that
You're saying
four proofs.
Set of different ways of proving. Right?
Yeah.
One is proof by
Contradiction and the counter example. Contradiction comes up more. Contradiction is the most.
Contradiction is probably most powerful and
Most perfect. Yeah, more heavily used way of proving things. This is this is also counter example. This is a proof by counter example. Yeah. Also, it has the element of contradiction as well. Okay, so that this is gone. Then there is something called, okay, so let me go to the theorem. So theorem 1 for today. And what is the topic of today? So our topic, we'll have many topics. Lecture 7 will not be totally about this thing. So lecture 7 goes here, and this is topic 1. And this is subtopic 1. This is subtopic 2. Here's the theorem. So the theorem is the sufficiency condition. Let F is a scalar field such that d1F. So I'm not writing again the scalar field. Okay, let me write it because it's okay. So you can. We are going to be restricting ourselves to 2 dimensions for obvious reasons, such that d1F, d2F, d12F, and d21F exists. Be careful about these things. And this is 21F exists on an open set as if A comma B is a point in S at which both d12F and d21F are continuous. We have d1 comma 2 F A B, obviously d2 comma F A B. So when you look at the theorem, it kind of makes sense to expect this. This is the most zeroth idea you should have in your head. That's true. No level of sophistication required. And the proof is also similar. It's a very simple proof. So we first construct a rectangle, which is A plus H, B, okay, B plus K. So I'm going ahead. Okay, please stop me if you have a question. Yes.
Great.
Yeah.
So we're saying that it exists on what is meaning the boundary of the set, not inside the set.
Open set. When we say open set, it doesn't have a boundary. It is obviously interior of the set S.
So then we can also use the term E. Right? Is there any different?
Open set. When I say open set, that's int S, the same thing. Open set is, yeah. So the interior of a set, the only reason we needed the definition of interior of a set so that we can define open sets. Once we have the open sets, we don't need to talk about interior of a set anymore. By definition, interior of a set is equal to the open set. Similarly, we have the definition.
But we also define boundary of the open set.
No, there is no such thing of boundary of open set. Yeah, yeah. Boundary is needed to define the closed set. Yeah.
There's such a thing as a closure.
Yes, there is exactly, and that is also required for the closed set. The closed set is the closure of open set. So, okay. That requires the other definitions that we introduced, like limit points. They naturally incorporate in it. So if you have a boundary point, suppose this is a boundary point. Okay, suppose my S is this. Suppose. So it is definitely not an open set because I have the boundaries here. So boundary point here, it doesn't matter how small. Obviously, if you take a big ball, it is going to intersect points outside the set S. But it doesn't matter for the boundary point. At that boundary point, doesn't matter how small ball you choose. It is always going to intersect points outside S. This is one of the problems in apostole. right? Who asks you to show that a boundary is actually it contains both points inside S and also outside S, complement of S. Okay, so that's boundary is funny, interesting.
So you can use both on an open set or also in an open set.
Oh, the question was in or on?
Right.
Well, Apostle wrote on. On means setter. No, open set is both on the set. It's on the set. It's on the menu. It's on the menu.
Just on being the boundary.
Yeah, but yeah, okay. Exists in an open set. Maybe. I will have to look into it, but I'm gonna go for in. In also makes a good.
In is probably better.
Yeah, exists in an open set. It's interesting. That's a very good point. It's tricky there. Let RHK rectangle. Let RHK rectangle with vertices A plus H, B plus K, respectively. So I'm going like this. So that's why my respectively goes like this. And our HK is contained in S. So my S is something like this. This is how people draw an open set. Dash line, because the boundary is not there. But you need to put something at the place of a boundary. Because it's not. Okay. Now let another thing, some difference symbol, and that difference is constructed in this way. So you might think of it as coming out of thin air at this point. But later we'll see that this specific form is found by just playing with the various combinations that you can construct. So because we define it this way, we can now express this difference in terms of D1, 2F and also in terms of D2, 1F.
I think there's an issue. It will be A comma B, A plus H comma B.
A comma B, A plus H. Where's the issue?
In the picture.
Yeah.
A plus H. Where's the A comma B? A comma B. A is what is?
A plus H comma B.
Yeah,
Tuples. It is tuples. Because you are taking two X and.
I'm sorry. Yeah. Sorry. Yeah, that's my bad. These are tuples. I only went for one of them, right?
Yeah.
It's tuple. Very good. So it should be B plus.
K.
It should be B plus K, and obviously this is A, and this must be A plus H, B plus K. Thank you. So what I wrote was half truth, no? Yeah. These are all tuples. Sorry.
I read in mathematics, half truth is a concept that exists in mathematics.
It doesn't exist. Yeah.
I used to know this Bengali mathematician, Rabindranath. His name was. So anyway,
It exists actually. But in this case, what I wrote is I didn't got those coordinates wrong. I got half of it wrong.
আমি বলছিলাম আমাকে সে জিজ্ঞেস করছিল how is your PhD doing? I said, yeah, I'm trying to derive something, and it's almost there. Almost very mathematics, there is no such thing as almost.
This is completely wrong because there are proofs that I know of. I don't know for sure, but I know of that you need to bound the error. And they're almost there, but the bounding the error is still in the Navier-Stokes case. Terence Tao has constructed a method and they're bounding the error. So it's almost there. It's always true. I have no idea. In number theory, it's everywhere. Always they bound the error.
Yeah, I know.
I would have gone into an argument. I would have run into an argument with him.
He had a PhD in Einstein causality.
Oh.
And I didn't have a PhD, so I couldn't.
So Susskind went into argument with Hawking. When he went into the argument, he had no knowledge of black hole theory of Hawking. But Hawking was saying that information is lost. So Susskind was completely deeply shocked by it. তারপরে সে রিড করতেছিল, তারপরে সে হলোগ্রাফি নিয়ে কাজ করা শুরু করছে বিকজ অফ হকিং।
I think he wrote also in his book that
he had the bet with was it Kip Thorne or the bet that
Hawking bet.
No, Hawking had several bets.
Several
One was with, I think, one bet was that he thought that black hole
Wasn't there.
no, black hole would destroy information.
Yeah.
That's what Hawking thought initially, right?
Yeah.
But after holography, he actually said that no, black holes will preserve information.
Yeah.
And he conceived that. It was just not anyway.
But he also didn't believe in Cygnus X1 is a black hole. He didn't believe in that one. With Kip Thorne, he took a bet and then he lost.
Yeah, Hawking lost a lot of bets.
But it's funny bet because he worked on black holes and he says that okay, I don't believe it. Consider. So we have this thing. Any other questions here? Anything I dropped? Thank you for that one.
So you're trying to prove that
I'm
they're continuous, right?
I'm trying to prove that they are continuous. That I have that as an assumption. I want to prove that they are equal. Okay. Okay, so consider. I lost my thread. Yeah. G of x. Now, why am I considering this again? This is out of thin air for the moment. For x element to a plus h. Achha, nobody pointed me out that these ABs are tuples here, right? That is all right then. So I cannot give a vector sign. However, if I write an x, this is a single variable function. Or field. Now delta of hk, now it becomes g of a plus h minus g of a. Is it true? It is true by inspection, because if you take a and b plus k, is that true? AB has a, so let us write it down. Let me verify that this is true. What is this thing? So you have f of a plus h comma b plus k, that's the first one. Then you have a minus, well, so g has a definition of minus, exactly. So you have a plus h comma b, that is probably the second one, no? And then g of a would be f of, that is clear. It is clear, no? Okay. The next thing is, so when I have a difference of functions and I have something continuous around it, we just go ahead and apply mean value theorem, because we have the license to kill. In this case, it's not license to kill. License to apply mean value theorem. That's the mean value theorem for what case? In this case, this is one-dimensional mean value theorem. So, okay. So G prime. So it should be x, because it's one-dimensional, and x is that, and then you have h. Okay. So by one-dimensional mean value theorem. Okay. Next thing we can do, and I would not say it's x, it has to be an x1 for the mean value theorem, right?
X1.
And when I'm right, connected them বিপদে পড়বো
You have also defined that x is a point between a plus আছে so
Yeah.
I write x also
Yeah, আমি এই নোটেশনাল ইউজ না করি এখন, রাইট? না মানে well,
by
let me not use. I have to pick x was an arbitrary point. I have to now choose a point. Right? So let me, yeah. So better I write it this way. In between that, okay? ওইভাবে লিখলে টাপলের সাথে হয়ে যাবে, ওপেন ইন্টারভালের একটা ক্ল্যাশ হয়ে যাবে। So yeah. So okay. Sounds about good. And Tuhin Shaikh, is it? What's your name? Sorry, he's not Tuhin. I messed him up. Yeah. I saw him first time today. One class. What's your name? Jarif. Okay. If you have any questions, please ask.
I'm still watching the other videos to understand.
Oh. Okay, still ask me questions if you have. Okay. Okay. Now what is g prime of x1? We can again use mean value theorem for that. No, not for that one. Not before that. You have to put the values of g first. Let me first write it down and see how it makes sense. Does it make sense? Use the definition. G prime means that. So I should give them equations so that I can talk about them without referring to. So this is 1, this is 2, this is using equation 2. Okay. Now we can use again mean value theorem. Why? Because these are continuous. That is demanded in the assumption of the theorem. So again apply mean value here. H, but in this case what is changing is this coordinate. So it's k which is changing. So here now we are working in this, we are shrinking that to 0, approaching the one of the corners of this rectangle. So for my case is the left corner, left down corner. So this is d2 of d1 f, okay, and I will call it x1 y1 where, okay, not where, let me put here, by 1D mean value theorem again, yes, and y1 is in between b to b plus k, yes.
So is there any reason that two commas between x and b?
Between x and b, x1 and x1 and x1, x1. Yeah, I also noticed that. যে আমার নোটেশনটা আসলে getting into a trouble. I have to write it very specifically. I'm sorry, most of the time I'm pretty much reason the way I work. Most about ideas and less about subtlety. Sorry. So I'm very bad in writing things. That's all right. So what we have been able to show the delta hk can be represented this way. Okay. Now again, so we'll give it another we'll give this a name. We'll give this equation number 3, or thin, and I'm sorry.
That's okay.
Okay.
As long as everybody understands the points.
Okay. We can. Okay. So we can define. So we can start from the beginning, like G. We define. Consider G. We can also. So what was so special about G of X? You can say. Why not G of Y? Right.
Because we wanted to use one single variable.
That's a good. But we could also use it for Y.
Yeah.
And we're going to do it again. Because the strategy of the proof is what? So you want to prove that these two are equal, no? So you will try to approach the problem in the single variable domain, once in the x direction and another time in the y direction. Okay, so that's why first we did with the x direction.
I think in the problems of limit also we did it that way.
Exactly.
First we took the limit for x.
And then we
to 0, then
y tends to 0. Iterated limits, yeah, we could do that. Okay, so we found one side of the coin. Another side of the coin will be, so we can also do the same for a function of y defined by say h of y to be a plus h comma y minus f of, I think because I'm doing a plus h comma b, okay, b or a comma y, sorry, a comma y. Oh, I'm sorry, it's a function of y, so a comma h. So when I look at gx, I see that my function doesn't, well, my function has b plus k and b, so my function doesn't depend on y really. So here that's why it's a g of x. Here it is a function of y, so my function should not depend on x. So I would take a plus h and a such that I can write this delta in terms of hy. So my placeholder for y should be the limit points of y, like b and b plus k, such a way that I can express del in terms of g of y. Okay. So now that's the motivation to construct it, and this should be h of y. So it should be h of b plus k, or what?
b plus k.
H of b plus k minus h of b, because it's a single variable function, so I just take a limit of both points and we do that. So then the next step, what will be the next step? Mean value theorem. I'm not going to mention it this time, but I'm going to say that okay, this is true, because the same are logic gulo already same. Then use the definition here given, and you have f prime d1 d2 a plus h comma y minus d2 f a comma y. Oops, I'm again running low on time. Okay, it's using Shomikaran char equation char. So okay, so what is this? This is, I cannot say it's y1, no? I have to say it's y2, no? I have to say it's y2 because y1 is already taken here. So I cannot say it y1, I have to say it y2, and I have to say this x2 comma y2, this. These are MVT with y2 between b and b plus k, and x2 being a and a plus. H. Okay. Fair enough. And I missed an H here. There should be an H here. This is coming from mean value theorem. A plus H to A, so we have this H and we have this derivative corresponding to the thing. Question? Yeah. We're not feeling good. Okay, yeah, sure. Okay. No, that's fine, that's fine. Okay, so we have these two expressions. We have 3, so this is 5. So equating Samikaran 3 and 5, we get hk d2 d1 f of x y y1 and hk d1 d2 f x2 y2 this. hk drops off and one has this. Okay, that's it. But okay, if I want to go backward, so if I want to run the argument in the other way, say these two are, it actually doesn't, it's a sufficiency condition, so it goes the one way, it doesn't go the other way. When you can have d1 d2 of f, but that doesn't mean that they are continuous. No, we have this counter example. So you can have d1 d2 f at a point, but you cannot just say they are continuous just because they exist. I'm sorry? Okay, so if you have things continuous, you can say they exist and they're continuous. But if they exist only, that doesn't mean they're continuous. But if you go the other way around, if they exist, does it mean that they're continuous? I can also come up with an example where they exist and they're same.
Who exists?
D1 to F, but this mixed and D2 and this mixed partial derivatives exist.
Existence and continuous are different things, right?
Right, exactly.
Existence is whether they are finite at a given point.
Right.
Continuous means that whether, if in a small neighborhood of the point, whether they are like a smooth or not.
But limit must exist, and the limit must be the same for every.
So they're different ideas, right?
So one implies other. Continuity implies
Existence.
Yeah.
So my question is.
Existence doesn't itself implies continuity.
So my question is, okay, you have shown that if they're continuous, then those two things are equal.
Right.
Is there a condition that I can put on the function f such that it's the derivatives will be? It's something you.
Well, yeah. If f is smooth, then that's just trivially true. If f is smooth itself, is smooth, that means, well, that really doesn't make any sense, because that also means that the derivatives you're talking about are in continuous. So you have just function itself, it's not going to do it.
It doesn't have to be C infinity, right? It has to be C2.
But still, we're talking about derivatives of f, not f itself.
Right.
The thing is that function can be defined at a point, but when you're talking about derivatives, then you are taking other points around that point. So only
When I say something is smooth, I'm talking about.
more points around it. So only function will not do. Okay. However, there are certain spaces where the function needs to be defined, like convex set where I can join 2 points and that lies in the same set. We have not used that here, we just use open set, meaning in a sense that if I take 2 points, they will lie in that set. But you can even make it a weaker condition, or in a sense more strong, weaker than open set. Excuse me for weaker or stronger word. An open set can be a ball, but I can construct some smaller subset of it, which is some star-shaped region, where with respect to a point, all the lines will be inside. Okay? So that might be smaller than open set, but that might be a stronger requirement as well.
Anyway, carry on with block model.
Yeah, well, this is actually important because Taylor's theorem, what we are using it, is actually true for not just the open set, but for the star-shaped region, where I can draw some lines, and that line completely, with respect to a point, I can draw some star-shaped region, and I join 2 points with that line, and that line completely lies in that space.
What's the star region?
The star region, yeah. So we will pose the theorem. আমি লিখতেছিলাম কালকে, এখনো শেষ করতে পারি নাই। writing is আমাদের নোটেশনের সাথে যাওয়ার জন্য, না হলে আমি রেফার করতে পারতাম, কিন্তু so that it becomes easier for.
Maybe you can write on your on a piece of paper then.
Yeah. That's what I'm.
Rather than typing.
I'm not typing it. Yeah.
Then okay.
Yeah. But still, I'm a bit.
There's a lot of time to type the mathematical sentence.
Yeah. But ওটা করতে পারলে আসলে এটা মজাও ভালো, এটা that's also fun to do. However, the theorem that we have proved, or we have proven here, the theorem that we have proven here actually is we can make it even stronger here, with a stronger requirement. If D12 is continuous, D2 is continuous, then they are equal. You can see it almost not proving it, right? It should be true. Okay?
I have a question
Yeah.
regarding this proof. We are saying that x1, y1 and x2, y2 are 2 different points, right? On that square.
Okay, so here is a trick. They are equal,
But 2 are different.
because that's not a problem. The thing is that we will take the limit. We want to prove it at AB. We will take, because even to 2 different points, we are coming from the same delta. We're coming from the same delta.
Yeah.
Okay, then you take the limit here, which is h comma k tends to 0. Here is also you take h comma k tends to 0. So then this becomes
Since they are continuous.
exactly, since they are continuous. আমি কি ঠিক মতো লিখছি? Okay. So a bit stronger requirement. So it's a remark on the proof. A bit more, or a bit stronger, let's say. A bit stronger requirement can be imposed. A bit stronger requirement can be imposed. Okay. For the equality of mixed partial derivatives, and that's the theorem 2. So this is subtopic 3, theorem 2. So theorem okay, any questions?
What is it? A bit stronger.
That's what I'm going to write down. Well, so what it means that we are demanding, in the proof we are demanding that D12 and D21 are both continuous at the point AB. Both continuous. However, we can say only one continuous, not both. Okay. This is not natural and it can be shown. So this is the fun part of this. So say f is a scalar field such that d1f, d2f and d21f exist. So at this moment you might say, okay, why not d12 exist and d21 I'm selecting? I have to select one of them. So there is no bias right now, just I have to select one of them. It doesn't give me an edge actually. So to speak, in mathematics we are not cheating. Still, we will cheat, but not yet. Exists on an open set. There is a Terence Tao video, how to cheat smartly on number file, mathematically. On an open set S containing AB. So what we're doing here is, again, we're saying that let F is a scalar field such that these things exist on an open set S containing AB, and let Atho, okay, is continuous on S. Then D1 comma 2 FAB exists. So these things implying this statement, this exists, and D1 comma 2 FAB will be equal to D2 comma 1 FAB. No, we are not demanding D1 to is continuous. Only one of them is continuous. D21 is continuous. D12 is, we are not demanding anything. Not even existence. Not even existence. Not saying a word about D12. That's something. মানে একটা ধরলে আরেকটা যেমন এক কান টানলে আরেকটা কান চলে আসে এরকম ব্যাপার হয়ে গেছে এখানে। এটা শুধু অ্যাপোস্টলে পাইছে, এটা আর কয়েকটা সমসাময়িক বইয়ে পাই নাই। ফর এক্সাম্পল manifolds ওই বইয়ে নাই, analysis on manifolds by Spivak. It didn't do this. Apostle did it. Proof. So we are cool with the statement of the theorem.
So okay, what is this theorem again? So f is a scalar function. D1 of f, D2 of f, and D21 of f exist on an open set containing AB. Let D21 be continuous on the open set. Okay. Right. Then D12 exists. D21 exists on an open set and D21 is continuous. And that implies that D12 exists and D12 is equal to D2.
And they exist and they're equal. So in the proof,
But you're saying that D1 they exist on an open set. That's a very kind of at the second derivative D21.
yeah,
The mixed derivative exists.
Yeah.
Right? Okay.
yeah,
Sorry, I just wanted to get that.
yeah. So we are taking this part of the proof from the earlier proof. This part of the proof is there. We can just carry, we have derived this already. No? That is up to equation 5. So we take equation 5, the patch, and we just get it to that. No? This is we found in the earlier proof. Why we can do that? Because there we assumed that well, am I doing equation 5 or equation, it should be equation, equation 3, not equation 5. It cannot be equation 5 because equation 5 requires you to do D1, D2. I have to go back here, excuse me, equation 3, okay, because D21 is, I'm taking that to be continuous, okay. So this is not equation 5.
This column, I'm able to see which one is jam
Which one is equation 4?
of that H1.
That H1. Cool, everything is cool. I can take it, no? I can take this. Okay. Next step. Zayad, is it Zayad or Zarif? Sorry, Zarif. Everything's all right? Please ask me. If you don't have to worry about your background, previous classes. You just ask me a question. I will try to answer it. Okay. If anyone is more sloppy, it's me in this class. I'm very sloppy. Okay. So. Okay, so I just did that and I'm going to give it another name and it's just equation number 7, I hope. No, 6, no, I haven't used 6, so I missed 6. Okay. Now from the definition of D1, 2 FAB, we write so D2 of F H A plus H comma B minus D2 of F A comma B. So that's the definition of D1 to at so we are using D1's definition here. So from the definition of when I'm saying this thing, really I have what I mean. Let me make it more clear what I mean by D. I'm actually using this one. I'm actually using D1's definition on D2F. Okay.
So what is what is the intuition behind this?
No clear?
Only D1 comma.
I'm coming to it.
Right.
I'm sorry?
Sorry, D1 comma 2. So now you're changing that.
No, D1 comma 2 means D1 D2.
Oh, that's actually D1 or D2.
Yeah, but I'm using the I'm using the definition of D1. No, not. I'm taking one of the variables.
Oh.
So
What is the intuition behind this theorem?
that is not the intuition is very. This is one of the things that you cannot get by intuition. One of the things you would expect that things are continuous. Okay, if they are continuous, the derivative should exist.
Yeah.
Okay.
So
Well, not should. I'm sorry. Not should. If the function is continuous, derivative might not exist. Okay. But D1 to F, if it is exist and continuous, so that is fine. D21 is exist and continuous, that's fine. Then you might imagine that if they're both, if derivatives I'm saying, not the function. D1 to F and D21 F. Derivatives, they exist, they are continuous. So that you might assume that, okay, if they exist and they're continuous, there is no reason for them not to be right, not to be the same at that point.
sorry, I'm not following you. Can you repeat?
The derivatives exist and they're continuous. The derivatives, not the function. Because function can be continuous and the derivative might not exist. Derivatives exist and they are continuous. So you may assume that they are equal. Because they are
Which derivatives?
D1 to D21.
Yeah, you can go up a little bit. I'm just more asking you about the specific theorem.
Exactly.
If you're saying that D1 of F and D2 of F and D21 exist on an open set, right? And D21 is continuous.
Right.
Then D12
Yeah.
exists, and not just only does it exist, the derivatives commute.
Yes.
Okay.
At the point.
What I'm trying to say is that it's a very complicated statement.
Yes. It is
It's not a
not.
very symmetric statement.
Yes.
I'm just trying to get what is there an intuitive way of understanding this?
There is mathematical way of understanding this theorem. There is no
Well,
other.
I can see that I'm not understanding it works.
Well, I haven't proved it. It's a statement.
You
It's a,
start the proof, right?
yeah, I have started it, but here you cannot see. I don't think you can see from here that the proof exists. It's tricky. It's quite tricky.
Okay, why don't you say it?
So, okay. Any questions up to this point?
There's D2F A plus H, right? On the middle side, right hand side.
A plus H, yes. Sorry.
And this
Okay. So I need D2 F A plus H comma B, and I need these people. So I defined, okay. So I get them. So D2 F A comma B. So let me first define this thing. Again, from the definition, again, we can write the same statements, right? From the definition of D2 FAB. So, yeah. So because D2, I will use K tends to 0. Okay. There will be K, and there's a D2. Well, there's no D2 actually. This is F now. And there's B plus K minus F of A comma B. Okay. And D2 F A plus H comma B, limit K tends to 0, K F, okay, the same thing. Okay. So the statements are just copy paste of the first statement with appropriate subject from the definition of D2 FAB, okay, and the definition of D2 FA plus HB. Yeah. So I have to. Question? Why? I'm sorry. No. Which one? The question 9 number? Question, yeah, question 9 number. What is the problem? Because A plus H is frozen here. A is frozen here. It's one of the
means you're taking the derivative with respect to the second argument.
second argument.
That's why it's D plus A. The
Both
first argument you don't touch it. Okay.
D2 means D2 means the Y and D1 means the X.
D2 means Y.
Y direction. I'm approaching through it. Okay, good. Now, very well. We have all our ingredients. Now we from equation 7 I won't say. So let's consider. It will have some resemblance with equation 7. So let's find this thing. H. Yeah. Let me. So substitute 8 and 9 into this expression and see what you get. Does it ring any bell to you? What is this?
This is second.
Right?
Yeah.
By equation 1, I think.
Equation 5.
the definition should not be equation choi, should be equation 1 ek. We'll use later from equation choi. I'm just writing this as this. I'm writing this as this. This is the definition of the difference. Okay. But I have to make sure this is equation 1. Yes, it's equation ek.
Do you not understand the second line? 1 by HK.
I'm sorry, yes.
Where did this come from? The second line.
This line, where did it come from, right? Or this line, this line, yeah. So I'm plugging in these things from here. This was this thing. So let me use this pointer as Tibra once suggested. This thing is this thing. So I plug this thing, and I have not plugged one more thing. That is, I should be plugging in a limit, no? You're right. Now the equivalence is correct. Thank you, Zarif. In mathematics, things cannot be just dropped without reasons. No? Yeah.
This is K, right?
Yeah, this is K. K tends to 0. I'm just taking those respective expressions from here and just putting them in. Okay. Cannot leave anything behind without proper reasons. Everything's cool? Okay, so what is this? Now a little bit go back, and we have equation choi, and it tells us that this particular thing actually I cannot write it this way, no? I should be writing it this way, no? Everybody should be pointing me out that, oh, HK cannot be outside the limit. Well, actually that's not true. H can be outside the limit, K cannot be. But I can also take H inside because there is nothing, no restriction on H. This is no restriction on H, right? And H is a finite number. If H is infinite, that's a problem, maybe. That's a problem. Good, very good. All the subtleties, yeah. So once I presented a proof and I didn't justify, then others came in and they justified every piece of evidence. One has to justify if it is true for every real number. So every real number means there are irrational numbers. These are exponents. The proof was about exponents. So one has to show that this is holding even, so one has to be careful in mathematics. So we are good at it now for the moment. And then we have this from here. Then we can say, oh, acha, we can use equation choi and write this as f of x1, y1, right? Using equation choi, right? Just this thing was this thing actually. Let me go back and show you this. This is the thing, no? Just substituting. Yeah, exactly. There is no limits applied. Limits coming from here. Okay. So this is equation number, I probably would say 10. Let me call it 10 and write it this way. So, what we have been able to, what do we want?
We want to show that each partial derivative is
Equal. Okay. So we started with what? We already have this, now. We already have had this, and we want to find D12. We want to find D12. Okay. So how am I finding D12? So I am writing D12, I want to find this, so I have written this down. Okay, and look at this, what I have done. What I am computing is actually this part. Okay, and we find that this part is related to D21 already. Look, D12's, this is what I want to find, and this part I computed. This contains D21 already. I haven't set h tends to 0 by the way yet. Okay, so if this thing needs to exist and be continuous, okay, I need to show that, so we must show that, okay, that if I take the limit h tends to 0, because here taking h tends to 0 gives me d1 to f. In this expression, if I take h tends to 0, it gives me d1 to f. That's what I want to find now. So we must show, if I take this limit and take this limit, taking limit on this side really means taking limit on the right side, and that should be giving me d21 f a comma b. No? That's what we want to prove, no? Look at the statement of the proof. What we want to prove is this equality exists, and this equality in a single slingshot. We find that everything can be achieved with a slingshot. Exists, continuous, and they're equal. Okay.
Why are you writing x1 with the x?
Why x1, y1? Why am I writing it? Because it's coming from here. And here, acha, ekhane ki ami x1, y1 dini na? It should be x1, y1. Nobody pointed out. It is equation 6 theke ashche. It is a silly mistake. I'm sorry. Thank you very much. It's a silly mistake. We dropped ones from there. It's a point in between the interval. Ekta point. Pointed in. এটা কেন আসে? এটা মিন ভ্যালু থিওরাম থেকে আসছে। There exists a point between the interval a to a plus h and b to b plus k. Okay, so it could have been xy. Yeah, is a tuple, as a triangle. Okay, as a tuple is a triangle in between. Exactly, you're right. In between the triangle, right? Okay, in the triangle. But okay, but x could be arbitrary. So x1, y1 bolle we actually understand that okay, it's one point, exists one point, not.
It means 1 point.
Yeah.
X1 means 1.
Yeah, mean value theorem means there exists one point. So you could have more than 1 point, but it is true, but it is not guaranteed. Right? Subtle arguments also. Thank you. Okay, any questions? Okay. Do you have a hurry? Hurry?
Easy.
Oh, I see. She was also feeling bit tired. She was also feeling a bit tired when I came in. I saw that.
Two long classes, one after another is,
Yeah.
human attention is fine.
So I'm trying to come up with some jokes.
Human attention is fine.
Yeah. So there is a nice slogan: "Live the game, love the game."
Is it from Squid Game?
Yeah, it's from the T20 World Cup music. Live the game, love the game. Okay. So in this case, it would be like do the math, love the math. No, it's not forcing. You don't have to. If you do that, it might be more rewarding. You get more out of it if you love something. Okay, so we have it. Our goal is clear. Okay. So what is our goal really? What do I mean by clear? That means all the things are depending on D21. Okay. However, there is one caveat. I just can't go ahead and say this is true. I demanded that D21 is continuous, na? D21 is continuous at AB, I demanded. So you can say, oh, this is trivially true. So our theorem is proved. No? However, there is one problem. I am taking k tends to 0 first and then taking h tends to 0. We can, however, there is one little problem. As I take k tends to 0 in the y direction, I don't know how x is changing. Because I have not specified how x is changing. Okay?
I think that is where the first derivatives exist.
Yeah, but the problem is it cannot go away from the rectangle. If I am doing the k change, so the limit d21 exists, it means that I am taking, okay, so d21 when you write it, it actually has f of say AB, it really means that, no? It's a tuple thing. So you're taking both of the thing together. But here we are not doing the same thing. One at a time we are taking.
There's a sequence.
There's a sequence, yeah. So I have to make sure this x does not get away from the rectangle because they are not related. As a single variable function, they are not related.
So we have to make it double.
Yeah, we have to, yeah, exactly. So I want to just show you one thing that might be interesting. So if x1 tends to x bar, where this x bar is in between this limit such that it is in the rectangle, okay, as k tends to 0, okay, then by continuity of d21 f at AB, okay, we are done. In a sense, because this would be some x bar comma b, no? Okay, now I can easily go ahead and take limit h tends to 0 of this thing. And that's it. Because my x bar, because, yeah.
The k thing becomes h. Whatever you can.
No, so this line, oh no, sorry, no. This thing became this thing. Then on this thing I am taking h tends to 0. I am taking one after the other. That's what this means, no? Here I have to take one after the other.
We are constructing an arbitrary form such that if we are taking k tends to 0, then x bar also stays in the string.
Exactly. Yeah. But it's a single variable limit. So you're first taking y, not together. Not
I
right.
think there was a proof that if, I think you gave us a homework. That
Yeah.
If the two iteratives exist and also the two, I think, double limit and single limit. I think they said two single limits and one double limit exists.
Here we haven't said anything about single limits in the theorem. We said d21 exists. We haven't
I
said.
think they are, I think that means for the single limits first we have d1 and d2.
Yes, you have d1, d2, right? Yeah. Okay.
What x bar means
X bar. Okay, so okay. As you're taking the single limit y, okay, you're taking y smaller, okay, but you don't know anything about how x changes as you take y goes to 0. Okay, it could be some complicated function, right? X, how it depends on y, we don't know. Okay. If as I take y to 0, The x is in between the interval a to a plus h, within the rectangle. If that is true, then I can say that limit k tends to 0, which is this line. I can say when the k tends to 0, I will be able to get this. Because k tends to 0 now, this is okay. This is always okay, but x bar is there, which is bounded between these two endpoints, which makes this thing much better, which makes this thing go to this thing. This is not the same thing as this is as I wrote down before, that both the coordinates I take the limit at the same time. That's not a two variable limit, that's a single variable limit. Okay? So now your argument comes in. We don't know. This is not going to work because if we are not given this, if this is not there. Okay, we don't know.
The x.
Eh?
We limited the boundary of the x. Right?
It is already given. We didn't limit it, it's already given. But we don't know how x changes. We don't know. So single variable limits are tricky. Okay, you saw that one doesn't work out. The limit might not even exist if you take the limit. So, this might not even exist. There might be a situation where this doesn't even exist. So, okay, that's bad. So, however, we do not know how how x changes as k tends to 0. We don't know. Okay. Therefore, we have to resort to a different method, which is really talking about the continuity of D21 as a whole. Okay. That is, using the definition of D21F at AB, continuity of. যেটা আপনি বলতেছিলেন, I guess. So I'm going to take just 20 more minutes. 10 more minutes.
Well, you do have 10 more minutes.
Yeah, okay. Okay. Okay, the lectures will be actually uploaded. So if you like, you might just follow the arguments and take the notes later. This actually puts too much stress on the head. Taking the notes and at the same time focusing on the. So what is the definition? Okay, so the definition is this, that let some epsilon tends to some if small positive number, let me write it down, some positive number epsilon greater than 0 exists, some infinitesimal positive number exists. Okay, then the continuity of the 2,1 f ab means there is an open ball B2, okay, at the point AB with radius delta, okay, such that D2, 1 f x, y minus t2 comma 1 f a comma b less than epsilon over 2, where x comma y is an element of b2. Okay. So yeah. So this is in the xy plane. This is the radius delta. Okay, and this is the well, this is also xy plane, but this is in this function. So there is this map d21f from there to here, and here centered at again AB. It is also centered at AB. Okay, and this is radius epsilon over 2.
Or is say open two balls or n ball.
It's a 2 ball. Yeah, specifically 2 by 2 to mane xy, that's why it's a 2 ball. Okay, that's the continuity definition. Okay. Epsilon by 2.
I don't follow what is the open ball is.
Open ball means this. Okay, this is acha. This open set. This open ball means you can always construct using the Euclidean norm. It's an open set, and AB is the center of the ball. One is a sphere. Okay, but its boundary is, you have all the points. So it's not. It's a solid sphere. However, the boundary is not there.
Oh,
So there's an open ball means that.
like open limits.
Oh yes, open ball. Yeah, open limits. Right, open limits. Yeah. So for a ball, you need two things. You need the radius and you need the center. So now we can choose. We can choose H mod less than delta over 2 and K mod less than delta over 2. Okay. Why am I choosing it? Because in the xy plane, my rectangle is in the xy plane, no? So if I could shrink it less than delta over 2, that means my rectangle is within the ball. Okay. I can choose this, no? I can choose them such that it is inside the ball. No problem with it, yeah? H and K are both defined on real numbers, positive real numbers. So, actually, yeah, can define them. Okay, so that the entire R H comma K is contained in the ball. B2. I'm not writing the arguments. Okay, let me write it.
Okay, it's okay.
So take x1, y1 one point in that domain. Okay. Then we find that this must be, I'm writing the same thing, which is the continuity of D21. I have to prove one more theorem. It's good. Just I'm substitute kursiv pointer, nothing else. Now I am in the rectangle. In the rectangle, okay? And now look at one thing very carefully here. So when you take k tends to 0, okay, when you take k tends to 0 on this thing, okay, look at this one. So when I take k tends to 0 here, when I take k tends to 0, it's a function of h only. Here. Okay. Keeping h fixed. If I keep h fixed, this, if I take k tends to 0, this is only a function of h. Okay. So how is that relevant here? Because this thing, the same thing is this thing. If you go this thing, this is the same thing as this thing. So this is also a function of h. Okay. I'm going to use it here. So therefore, now keep h fixed and let k tends to 0 it should be some function of h. So it is coming from which equation? By equation 10, yes. By equation, by steps of equation, Dosh. Now the proof is now done. Why? Why? Because k tends to 0 doesn't bother this thing. Okay, h tends to 0 also doesn't bother that thing, no? And this part is unbothered. This part is unbothered. But this part goes to f of h limit. Now if you write down k tends to limit of this thing, after taking k tends to limit of this thing, what it becomes? Then we find that this thing instead becomes f of h. Yes. Okay. Which is also less than epsilon, no? If it is less than epsilon by 2, this is obviously less than epsilon. Is that true? It's not necessarily true, no? Not necessarily true. If it is less than epsilon by 2, epsilon is bigger than epsilon by 2. So you cannot say it's bigger than, but epsilon tends to 0. But epsilon tends to 0. So you can smear it out saying that, okay, epsilon by 2 is maybe the same thing. Epsilon is arbitrary. So even though I cannot say something is less than 4 means that less than 6. But I can say something tends to 0 less than something by 2 is the same thing as saying it is less than that something. Because the something tends to 0.
But if something is less than 4, something is obviously less than 6.
Yes, that is also true. Yeah.
So then it tends to 0.
Yeah. But you can say it for infinitesimal limit.
So we should probably wrap up.
Well, that is the definition of the continuity of D21 at AB. Can say that, no? In my head, I saw that differently, yeah. You're right. You can't just go by that if some better is epsilon. That's the limit of this thing. But x1 goes to h, comma b. So that's the okay. Yeah. Okay. So that means that this is the same thing as limit h tends to 0 f of h, which is g21 f of ab. So that's true.
You didn't get the second last line.
Second last. Which one is second last? This line or this line?
Yeah.
This line.
No. Yeah. I.e.
Oh, that means
Yeah. I get it, but what is?
this is okay. This is the definition of what does it mean by limit of. So this is this thing. It's a definition হচ্ছে এটা. When you say this is what Tibra sir was asking. Huh? But limit, okay, so when you say limit of a single variable exists, that means there is some epsilon delta.
Yeah.
Okay, so your delta is here because we have already said that we will take h and k to be less than delta by 2. So there exists delta by 2, again the delta and delta by 2 is the same thing. For the infinitesimal limit it doesn't matter. Okay, well, okay. There matters, but it is arbitrary. The epsilon deltas are for infinitesimal. We are ultimately taking it to 0, so they are all rationals. They are very dense. So both of them will. So the whole point is that they're converging to 0. So it doesn't matter you take that or divide by any finite number. It will take to 0. Yeah, that's done. Okay.